Okay, so all right, your lab, like I said, was posted online today, and it's going to cover some of this stuff. So, little review of Thursday's class. On Thursday's class, we learned a couple of new terms. We learned the term lyophobic and lyophilic, hydrophobic and hydrophilic. So very quickly, I'll just remind you of those terms. Phobic means no attraction. I think literally in English, phobic kind of means you have a fear. And I mentioned arachnophobia would be the fear of spiders. I think there's other ones I can't remember, like fear of closed spaces or fear of heights, but typically it's a phobia. So a lyophobic substance is just it's not really to say, you shouldn't really say it's afraid of, but it's not attracted to the dispersion medium. A lyophilic substance is attracted to that dispersion medium. So something that's lyophobic, it's not attracted to what it's dissolved in, would typically be a poor colloid. It would be easily precipitated. Something that's lyophilic, though, something that has, Naim, you just brought up something that's pretty gross there. The fear of like, it's tryptophobia or something, the fear of like small holes. Very creepy images online. But anyways, we won't talk about that. Sorry. So lyophilic, these are substances that do have an attraction to their dispersion medium, like the solvent you could think of. These are very stable colloids. They're hard to precipitate. Now, we can really make this make sense by talking about water. And these hydrophobic and hydrophilic, these are more important terms. Hydrophobic is something that is not attracted to water, like oil. So oil being nonpolar is a hydrophobic substance. It is not attracted to water. Hydrophilic, this would be something like a salt, like an ionic compound, or table sugar. These are attracted to water and they dissolve easily. Okay, so hydrophilic substances don't actually make very good colloids because they would make a homogeneous solution. Which you learned a long time ago in chemistry, something like salt water or sugar water. They're typically homogeneous mixtures. Hydrophilic substances do not dissolve and they can make really nice colloids, meaning they can be dispersed throughout the water. An emulsion is a really good example of this. An emulsion is something formed like between oil and water. They're not supposed to mix. We can help them mix and they form an emulsion, which is a big problem in the oil and gas industry. For when you're refining petroleum, you don't want water there. Water can cause problems, can corrode things, cause side reactions. So hydrophilic substances, oil and water, they can form an emulsion, which is bad. Okay, so this brings me to our new topic. This topic is in lab 6, and you'll need this to answer your lab today or tomorrow or whenever you do lab 6. Okay. Oh, and by the way, wink, wink, wink. This is definitely going to be on your final exam. Lab number 6, or sorry, this concept of soap is very important for your final. So let me explain it. I'll read a few things. I'd hope to get through most of surfactants and then we'll check the time. I don't know if I'll get to section 114 today, but we'll do a little bit. We're almost done this course, by the way, which is good. Okay, so soap and detergent. Well, first, let me go back to this slide. The ability for a soapy solution to act as a detergent has been known for hundreds of years. So soap is this chemical. Typically, it forms like a slippery substance. It's bubbly or slippery. It's been known to act as a detergent, meaning a cleaner, for a long time. What soap actually is it's a salt. So it's kind of like ionic between a fatty acid And it can act as a surfactant, which I'll talk about today, meaning it can emulsify oils, enabling them to be carried away from water. Now, even before I get into this, I can explain to you a quick experiment you can do in your kitchen. Go to your kitchen today, get 2 plates or a bowl, 2 bowls, and put a little bit of cooking oil in each bowl or plate. So olive oil, could be ghee, could be canola oil, vegetable oil, whatever. Put a bit of oil on the plate or bowl. Wash each plate, but in one plate, just use water, and on another plate, use soap and water. And you will immediately see a drastic, a significant difference. The plate that you use soap, the water will really clean the soap away or the oil away much easier. You could do the same thing with your hands. Put oil all over your hands and try to wash your hands with water, or put oil all over your hands and try to wash your try to wash your hands with soap and water. And you'll notice your hands will be much cleaner because you use soap. The way that soap works is actually hilariously simple. There are antibacterial soaps out there, and this is a relevant topic because, it's Corona, COVID times. Such a weird time in history where we are washing our hands more and more. Antibacterial soaps are different than old or classic soaps. Antibacterial soaps have things in them, typically alcohol, which kill bacteria, which break apart the wall of the bacterial organism and literally kill them. Old soaps work just as well, but they work in such a different way. A classic soap, and this is hilarious how it works, it makes your hands so slippery, literally so slippery, that the oil or bacteria cannot stick to your skin. So when you wash your hands with soap and water, the water helps the bacteria or oil slip away. So soap makes your hands slippery, which cleans your hands. It's such a simple process. There's no crazy chemical reaction on the surface, no crazy chemical reaction. It's just making your hands slippery so the oil or bacteria slip away. Now, of course, this is chemistry 2420. We're going to get a little bit more complicated here. Soap is really cool. Soap has the ability to mix with water and oil. The reason it can do this is because soap molecules have a hydrophobic end and a hydrophilic end. It is a surfactant. Well, I'll talk about, maybe I'll wait for a minute, but I'll talk about the definition of surfactant in a minute. But the idea for soap, here's the soap molecule. This is sodium stearate. This is typical chemical found in soap. Look at this crazy molecule. It's so big, it's so long. One end here is nonpolar. This nonpolar end is hydrophobic. This would be the tail. The head is hydrophilic. This is polar. So the cool thing about soap is that it has this nonpolar end that can attach to nonpolar substances like oil, but it also has a polar end that can attach to things that are polar like water. So the soap is attaching to oil, it's attaching to water, and it pulls the dirt away. So you do not need to draw this, do not worry, but you should know that soap has a hydrophobic end and a hydrophilic end. It's attracted to nonpolar things and polar things. It's real cool. So when grease or dirt or oil is mixed in with soapy water, the soap molecules will arrange themselves. They will surround, if you know what I mean by that, like they'll gather around into tiny clusters called micelles. Now, I promise you, I will ask you how soap works. The level of detail that you go in here is up to you. Like what I'm saying is, I don't need you to write me an essay about soap. Soap has a hydrophobic and hydrophilic end, meaning it can attach to nonpolar and polar things, so it can be washed away. That's really the easiest way. But if you wanted to be technical, what's happening is the soap are forming these little clusters, aggregations called a micelle. It's breaking the colloid. It's breaking the shouldn't say it's breaking the emulsion. It's actually forming the emulsion. Sorry. So a micelle is an aggregate. Remember what the word aggregate means. It means several things grouped together. So what a soap does is it forms an emulsion. It mixes the oil and water. Boom, you can wash it away. Now I have a picture of this. Don't worry. I'll explain what a micelle is. Sounds like a French word, doesn't it? So a typical micelle is in an aqueous solution. It forms an aggregate, a group, a cluster, a blob, B-O-L-B. I don't know if you guys know that word. Blob is like an old horror movie where this big giant blob, this cluster of goo kind of kills people. Old, really like old 1950s movie. But anyways, it's a group or cluster. And the hydrophilic head surround the solvent and isolate the oil, the hydrophobic center. I'll explain this. I have a picture of this. So the water-loving part of the soap molecules stick to the water and point outwards. They surround the outer surface, putting the oil in the middle. I will explain, like I have a picture. So the oil-loving hydrophobic part of the oil sticks to the oil and traps it in the center, forming a little cluster of oil that can't come in contact with the water. With the oil packed away in the center, the micelle is now soluble. We've formed an emulsion. Oops. And the soapy water can be rinsed away. Remember, emulsion is a colloid between two liquids. Okay, so oil and water is a great colloid or emulsion, two liquids mixed together that shouldn't be. Here's a picture that I hope helps you understand what's happening. They almost look like creatures, don't they? They almost look like little squids or jellyfish. Trust me, they're not living creatures. They're just molecules. But here I have my polar head, which is attracted to the water. And what they do is they line up forming an aggregate. This is called a micelle, or a group, a little blob of oil. The oil is in the middle, and the hydrophobic heads surround the blob of oil. The hydrophilic tails are in the middle. They surround the oil and allow it to be carried away when you wash your hands with soap. This is basically exactly how they look. Yes, and I am. Now, okay, let's be more specific. These do look like little sea creatures. Realistically, the tails would be hydrocarbon chains. And we know hydrocarbon chains are kind of like, I don't know how to explain it, but they go up, down, up, down, up, down on an angle. The micelles here kind of look squiggly, like they have no pattern, right? Like they look like little creatures, but realistically it would be, hydrocarbon chains that have a distinct pattern. But yeah, this is exactly how they look. Pretty cool, pretty weird. Again, it's kind of creepy, but like, before I taught chemistry, or before I was a chemistry student, I never thought about soap. I wash my hands 3, 4, 5 times a day and never think about how it's working. Like after some time when you haven't showered in a few days and your hair feels oily, if you took a shower with just water, it wouldn't work. Your hair would still be a little oily or greasy. But when you use soap, these micelles are forming around your hair, trapping all of the oil and grease in your hair and carrying it away. Pretty cool. So yeah, that's it. This is definitely a test question. And remember on a final exam question, and just remember on your final exam, don't go too crazy with your definition. The simple way to define this is soap has a polar end and a non-polar end. This allows the soap to mix with polar water and non-polar oil, forming an emulsion that can be carried or washed away. So let me say that again. Soap have a non-polar and polar end. The non-polar end mixes with oil. The polar end mixes with water to form an emulsion. The emulsion can then be washed away. Oh, so Niam, the good point, you use shampoo, not soap. They're essentially the same thing. Soap and shampoo are the same kind of idea where it's a surfactant. The difference with shampoo and why you should use shampoo or conditioner and not hand soap in your hair is shampoo is pH balanced and has other chemicals in it to keep your hair healthy. Regular soap, like hand soap, can dry out or hurt your hair because hair is such a complex compound or thing. And don't ask me too much about hair. I'm not a biologist. But soap is hair is a little bit more delicate than your skin. So you would use a pH, properly acidic or basic balanced chemical. Anyways, okay, cool. So, okay, what else do I want to do? Okay. It's 3:55. We have lots of time. So what I would like to do is talk to you about the 4 different types of surfactants, and then maybe we'll kind of take a break here where I'll talk about colloids in the petroleum industry. So let's just kind of talk about the different types of surfactants, and that'll be it. All right, let me check the chat. Yeah, there's different shampoos and things you can do for your hair for if you're losing hair or your hair is dry. I know a lot of the ladies in this class might have long hair and deal with split ends. There's even shampoos out there that help keep the dye in your hair if you ever dye your hair. Anyways, I won't talk about hair much more, but it's interesting. Kind of makes you wish that your when you go to your hair salon that your hairstylist knows a bit of chemistry because they could tell you what chemicals are good for your hair. Anyways, that's a whole other topic. So I just want to briefly define one more term and then we'll go back to surfactants. Okay, one term, guys, this is not a term that you need to study, this term of absorption, but it will help me kind of explain some things in the future, but not on final. So let me just very quickly talk about absorption, and then I'll get back into surfactants. Adsorption, adsorption, is the adhesion of atoms, ions, or molecules to a surface. Key thing, and this is hard because I know you guys speak 2 languages. Absorption is not the same as adsorption, which is kind of confusing. But adsorption, AD, is related to the adhesion of atoms on a molecule, atoms, ions, or molecules onto a surface. Adhesion means glue or stick. So the chemical process of adsorption is when atoms, ions, molecules start to stick to a surface. This process can create a film on the surface. So, think about when you lubricate something mechanical, like you're adding a lubricant to your engine, you're adding a lubricant to like a hinge on a door. That lubricant, that oil, typically sticks or adheres to that surface. Glue is another example. You glue something together. Glue is helping it stick to the surface. So the adsorption of water is really important in chemical engineering because okay, I'm going to see if you guys are awake. Can you think of this? What would be a problem? Think of metals. Okay, think of everything you've learned about at the college with metals. What could be a problem if water is sticking to metallic surfaces? There's a one-word answer for this. What would be a problem if water is sticking to metallic surfaces? One word answer, and it starts with C. Think about the reaction that can happen with metallic surfaces and water. It's not good. Yeah, and I am 10 out of 10. Beautiful. And Ali, beautiful. Corrosion. You do not want water sticking to surfaces in a any type of industrial environment. You want to keep things dry, clean. I know a huge problem in oil and gas industry or marine industries is salt water sticking to surfaces. Corrosion can be a big problem here. Now, I told you adsorption isn't something on your final, but you should consider the problems of corrosion in industry. If you're, working on an offshore oil rig, you're working in the ocean, the Gulf, where it's salt water. If you're having salt water kind of cling or stick to metal surfaces, that can cause rust or corrosion. So it's bad. It's bad. Well, and I am. Yeah, you're right. It is the same thing. Oxidation and reduction are directly related to corrosion. Corrosion is a redox reaction with oxygen and metal. Brilliant, brilliant. Okay. So again, think about oil and gas. When you're drilling in the ocean, offshore, and you're drilling for oil, a lot of that gets mixed with salt water. You add salt water to all this metal equipment, metal pipelines and metal distillation columns, you're introducing problems for corrosion. So you don't worry, you don't need to study this slide at all. I'm just going to skip past this, but just keep in mind that when you're having water stick to surfaces, specifically salt water, because salt water will help with your oxidation and reduction, it's bad. Bad, bad, bad. All right, 4 o'clock. Here we go. Just give me 5 minutes or so. We'll be done. I'm going to give you another good hint today for your final exam, a good wink moment about something you should consider. First of all, surfactants. This is, again, will help you for Lab 6, which is online for anybody who's late. Lab 6 is online right now. Check your D2L. What is a surfactant? I've been talking about surfactants for the last 50 or 30 minutes. What is it? Soap is an example, but there are much more examples of surfactants than soap. Surfactants are compounds that lower the surface tension between two liquids. Now, think about that when I'm talking about soap. Oil and water do not mix. They they have surface tension that separates those solutions. They do not mix. So what a surfactant does is it breaks that barrier down, literally, and you'll see this in Lab 6. I'm very happy with Lab 6, by the way. I honestly think Lab 6 is better as a video than it is as an experiment. I don't know if that makes sense, but very happy with this. You'll see in Lab 6. In Lab 6, I used two chemicals to try and break the surface, to break that little layer of oil and water. And I successfully do that using soap and something that you might not have ever thought about. I used an egg, like an egg you would eat. So you can watch my lab video. Again, I'm very happy with it. So surfactants, they can be detergents, wetting agents, which help get oil to absorb water, emulsifiers, and foaming agents. They're the big ones. Surfactants can help emulsify two liquids, so liquid plus liquid, or foam, liquid plus gas. I mentioned the other day, there are two types of colloids you really need to know. Emulsification or emulsified, that's a liquid and liquid mixed, and foam, That's a liquid mixed with gas. Or more technically, it's a gas dispersed through a liquid. A good example of a foam would be like whipped cream. Okay, you'll see that in Lab 6. I actually whip up something in Lab 6. I'd say half of Lab 6, guys, is basically a kitchen demonstration. I use things like cream from Tim Hortons, eggs from my kitchen. It's a pretty cool little experiment. I have a laser. If you guys like lasers, there's a laser in Lab 6. I mean, it's super cool. I'm very happy. Okay, anyways, 3 quick slides and we're done. So when surfactants lower the surface tension, they basically make water molecules real slippery. And they're less likely to stick to themselves and they're more likely to surround oil and grease. So again, forming these micelles. Because surfactants like soap have a hydrophilic and hydrophobic end, it makes them effective cleaners. We already talked about this, but wink, 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 wink. I'm going to ask you guys, why is soap a good surfactant? And this is why. So huge stars everywhere. Star, star, star. All right, the finale. Oh, and sorry, Niam asked a good question. Was I at home or the lab? I could have done this at home, but I did it in the lab because I needed one little piece of equipment. And there was one chemical I was using that was a little bit risky. I was using cyclohexene, which is not something I should bring home. So I did do this in the lab, but honestly, I could have done most of this in the kitchen. Like almost 80% of the lab, I could have done in the kitchen. Or more, maybe 90%. Anyways, here we go. Last part, 3 slides. Guys, this is definitely multiple choice type question for your final, and it's so easy. Okay, this is a gift, really good type of question. There are 4 types of surfactants you can see. They sound complicated, but it's not, especially if you have a little bit of a memory of chemistry 1120 and 1121. There's anionic, non-ionic, cationic, and amphoteric. Now, I can explain this in under 15 seconds, maybe under 10 seconds, okay? Anionic surfactants have anions. Non-ionic surfactants are no ions or have no ions. Cationic surfactants are made of cations, and amphoteric surfactants have both. So remember, anions are negative, cations are positive. So anionic, negatively charged, cationic, positively charged. Non-ionic do not have ions. Number 4, amphoteric. You learned about this in chemistry 1121. Amphoteric means it's both. There's cations and anions. In chemistry 1121, you learned amphoteric was a substance that can be an acid or a base. Your simple definition of acid and base is acids are positive protons, bases are negatively charged anions like hydroxide. But you don't need to know that. So let me kind of quickly go over these 4, and I'll kind of explain to you how I would ask this on your final, and halas, we are done. Anionic, surfactants containing negatively charged ions, okay? They are typically insoluble at low temperatures. They do have hydrophobic effects when they're in warm water. You don't need to know that. All you need to know is that anionic substances contain negatively charged ions. Non-ionic have no ions. When they're dissolved in water, there are no ions, which means they are very stable, but they don't react well with ionic compounds. Okay, ionic things like to react with polar or ionic compounds. Non-ionic, they don't really work very well with acids or electrolytes. Electrolytes meaning they have positive or negative ions. Okay, cationic, well, these are surfactants that have cations. There you go. Their functionality is not typically consistent with ionic or anionic compounds. These are really good surfactants for cell membranes, which means they are very good in hand sanitizer. So cationic surfactants, if you have a hand sanitizer that doesn't have alcohol, remember, soap doesn't kill bacteria. Most hand sanitizers will have ethanol, which is alcohol, which kills bacteria. It's a good sterilizer. It kills germs. But sometimes people want alcohol-free sanitizers. It's better for your skin, for example. So when you buy a hand sanitizer that says it's alcohol-free, if it doesn't have alcohol, how does it work? It's typically a cationic surfactant. Okay, so not really relevant for your final, but cool to know in the Corona times where we're washing our hands so much. If it doesn't have alcohol, how does it work? It has a cationic surfactant. And then the last one, amphoteric. Amphoteric means both. It would have an anion and cation ions in its surfactant. You can almost think of amphoteric like your Class C fire extinguisher. Remember back in your safety lab many years ago, you learned like there's type A for paper, type B for oil, type E for electric. Type C just works for everything. Amphoteric is like that. It's a bit of an all-purpose surfactant. So, when I told you guys that you might need to know this for your final, just think about this question. Okay, imagine we're looking at slide 110 and here are your options. Options A, B, C, and D. And I'm going to ask you guys on your final, which type of surfactant contains no ions? What would you pick, A, B, C, or D? I'm giving you a minute to tell me, but
B, of course.
yeah, B, of course, exactly. It's kind of a silly question, isn't it? Which type of surfactant would contain anions, or like only anions? You would say A. Which type of surfactant contains both? You would say D. So very straightforward. Okay, guys, that's it for me. We're going to finish here. We'll apply this to the petroleum industry tomorrow. Talk about oil field emissions or emulsions, sorry, and emissions, I guess. And just a reminder for the people who showed up late, Lab 7, I'm going to make a posting on D2L right now. Lab 7 is next week. Lab 6 you can do online this week. All right, so we're done. If you have any questions, let me know. If not, have a fantastic day.